In mathematics, when we talk about independent events, we're talking about events that have no impact on each other. So if you like, these are the opposite of conditional events. Now, here up on the slide, I've got the formal mathematical definition of what independence is. Okay, so let's just go over it. And then we'll kind of try and unpack it and explain why it's defined in this way. So A and B are said to be independent if the probability of A times the probability of B is equal to the probability of A and B both happening. Now, if it was up to you or I, this is probably not a good definition of independence. This doesn't kind of imply anything about A and B and which one, the fact that they don't have an impact on each other. However, this definition flows kind of out of a couple of different ways of thinking about this. And I guess in this video, we're going to talk about how this relates to those definitions. So let's just think in terms of common sense what it means to say that two things are independent. We've just talked about conditional probability, so talking about the probability of A happening given that B has just happened, or the probability of B given that A has just happened. We've just talked about a bunch of those. What would these mean if we said that they were independent of each other? In other words, that they didn't have any impact on one another. In other words, if A happened, it wouldn't affect the probability of B at all. Okay, like two completely separate events. That's what we mean by independent. Okay, and the way I would represent that mathematically is what I would say, well, the probability of A given that B has just happened, well, if B doesn't have any effect on A at all, probability of A given B must be the same as the probability of just A. That makes sense? Like whether B has happened or not, A still has the same probability. And similarly, I don't know what's happening with my writing there, the probability of B given A, well, it must just be the same as the probability of A, of B rather. Okay, so the given bit doesn't make a difference to the probability. Okay, if B has happened, A still has the same probability. If A has happened or not happened, B still has the same probability. This is what we mean by independent. And if we take this little bit of information, this bit of knowledge, okay, we can get to this result. And in a couple of ways, and I'll show you how. The first way is to think about a probability tree. So let's, I won't try and do it quite that wide. Take a probability tree. First, A is going to happen or not happen, and then B is going to happen or not happen. Now, I'm not going to worry what the probabilities in particular are. We're talking generally here, but A is going to happen or not happen. It's going to have some probability. There's going to be some probability of A happening. This branch represents the probability of A not happening. Now, in this next branching, this line represents the probability of B happening given that A has happened. And I could put labels on all these other ones, but this is the branch I'm going to look at. Now, if you have a look at our independence definition, probability of A times the probability equals the probability of A and B. Okay, well, the probability of A and B is represented by reaching this location on the probability tree. A happened, then B happened. This is A and B. And to work that out, I would have to do these two things times together. The probability of A times the probability of B given A. But if these things are independent, we know that the probability of B given A has to be the same as the probability of B. And so if we work that out, I can replace this guy with just probability of B. And that is the definition that I had for independence. So that's one way to kind of see how that relates. The other way to see how this formula drops out is by thinking about the conditional probability formula. So in the conditional probability formula, probability of A given B is equal to the probability of A and B over the probability of B. And as before, we said probability of A given B is equal to the probability of A. That's what independent events mean. So this can be replaced with the probability of A. And once again, very similar to before. This becomes probability of A equals that. And if I multiply across, I get the definition of independence. Now it's important to have a good concept of that, of both those things, kind of in your head what independence means, but also this rule, because this rule kind of becomes the benchmark, it becomes the test for how we tell whether or not two things are independent or not. You multiply their probabilities together, and if you get the same as the probability of both of them happening, then it means they must be independent.